All right. Good afternoon. Any questions? Any comments?
In the discrete symmetry translation, we get block theorem rather than a translation symmetry. Why is that? Like conservation of momentum? But we get a block theorem which also is a conservation of momentum, but it's a different momentum.
Because, generally, like conservation laws emerge, at least classically, when you have a continuous symmetry, right? There's like a famous theorem called Noether's theorem. When you have a continuous symmetry, there's like a corresponding conservation law. This is not the case. Like this theorem is valid only for continuous because it's put like that way. When there is like a discrete symmetry, you don't have that. But like this is technically sounds complicated, but in practice, what happens is like in the periodic potential, what you have is like you have like electron, and you also have lattice. What can happen is like electron can bump into lattice and get as much momentum as it wants, or it can bump into lattice and it can give as much momentum as it wants to give. That's why in the periodic case we don't have a momentum, but we have so-called quasi-momentum. And the quasi-momentum is this lattice momentum, and it defines like so-called Boolean zone, and you can also like have things like so-called Uncoulomb processes, which doesn't conserve momentum because lattice can provide it. So it's very technical. If you want to learn this, I suggest you can take 409.
Yeah, like in those continuous symmetries, we have the generators like momentum for translation symmetry.
Yes.
If the symmetry is continuous, why do we have exponential generators?
Like if that's generally the case. If you have a continuous symmetry, that means you can apply a little bit of that symmetry. Like you can infinitesimal application of symmetry is possible. That means there's like a generator, right? Like we are going to see this through examples. In the case of translation, the generator is momentum. But what is happening in the like discrete case, momentum is still generating the translation, but that translation is not a symmetry unless it is these discrete units. So I want to like introduce like a second example today. If there are no other questions, I want to talk about parity, or sometimes this is called inversion symmetry. I think the book calls it like parity extensively, so I'll call it parity. And let's start with one dimension. Like if you remember, in 2 dimensions, a parity application corresponds to rotation by pi, so we are not going to, we can also consider a kind of inversion in 2D, but generally when people say parity, they mean either 1D or 3D, and that's what we are also going to do. And what is the program? You have like some operator. Let's use uppercase sigma for parity, and it acts on functions like psi of x, and it gives us a new function psi prime of x, right? This prime tells us it is transformed, and in the case of parity, what we have is psi of minus x. And you can apply this parity twice. For example, you can do it pi squared psi of x, and right, one application is going to give minus, one more application is going to take that minus back, so you are going to have psi of x back. That means, right, this times function is function itself, like there's here 1. That means eigenvalues of this parity, what are they? If 1 or minus 1, yes, thank you. Also from here, right, because this is 1, we also see pi to the minus 1 is equal to pi. Okay. So let's also think about the Hermitian conjugate of parity. Like let's use bracket notation. There is like some f function, and there's parity acting on some g function. And what this means is like we have the x, f of x star, pi of the operator, and g of x. and this goes from minus infinity to plus infinity. That's the definition of this bracket notation. And after the application of parity, what we are going to have is that this x is going to go to minus x. Right? So I'm trying to find the Hermitian conjugate of parity by using our program from 300. And now I want to change the variable in the integral. I want to call some x tilde is equal to minus x, and the x tilde is going to be minus dx, right? Then I can just copy this line and do the change of variable. So there's like x tilde because of this minus, there's this minus, and x is minus x tilde, and minus x is x tilde. And anything else I should do after I changed the variable in an integral? The domain, yes. It goes from minus infinity to plus infinity, so it should go from plus infinity to minus infinity. Okay? But now I recognize, so this piece is actually, right, x tilde is just a dummy variable. Right, once I'm done with this change of variable, I can forget about tilde, but I'll just leave it as is. But this piece is the parity acting on f star. Okay, this is plus infinity to minus infinity. So this is one thing. And also, I can flip the integral limits. And if I flip the limits, what should I do? Like I flipped, it was... Exactly, I have additional minus sign, so this minus sign became plus sign. But this final result is exactly pi acting on f in the bra space with g. And this is exactly the definition of Hermitian conjugate, right? You just carry something to this side, and whatever form it takes is the Hermitian conjugate. And from here, we also see psi dagger is equal to, or pi dagger is equal to pi. So it's both, and also because of this, it's equal to pi to the minus 1. So this is both Hermitian and unitary. So parity is like that. So let's think about operators. So of course there are two operators, but in the general case, q prime, if you remember, changes like pi dagger, q, pi. We argued why this is the case last time, and I'll just consider x and p. In the case of x prime, so this is pi dagger, x, pi. Maybe I can be a little bit pedantic because we are just starting to warm up, and in the case of p, I won't be pedantic. So how do I deduce what happens here? I just take this entire thing and hit on a function. Like there's like a f of x. And this thing is going to be, right, so this piece, I'll just apply term by term. Pi times this is f of minus x. And now I call this, I don't know, some intermediary function g of x, and this x hat is going to go and find whatever the variable is. So this is going to pull it out. So this is pi dagger x. Now I'll just write gx, but gx is f of minus x. And now I can apply this pi. This is going to be minus x f of x. But minus x is equal to minus x hat acting on f of x. From there I deduce like so many lines to write something obvious, but that's fine. So this is minus x. Okay? So as an exercise, you can try to convince yourself p prime is going to be also equal to minus p. Then any function, any operator of x and p, let's use the alternative notation. We'll go to, under parity, q of minus x minus p. Good. So this is the definition of parity or inversion symmetry, and we say that we have inversion symmetry. We have inversion symmetry in our system if, what was the condition? Exactly, Hamiltonian, right? Hamiltonian is special. I need to use h prime is equal to pi dagger h pi. Okay, these are operators, but let me not write it because almost everything is operator here anyways. And there's inversion symmetry means h prime is equal to h, right? And I can write this, this thing is equal to h. Multiply both sides with pi. What you are going to find is h commutes with pi. So that's when we have inversion symmetry in our system or parity. And since we just showed, right, p goes to minus p, and in the Hamiltonian we have p squared over 2m under parity will just go to itself because of square, p squared over 2m. Then the only requirement for us to have inversion symmetry is v of minus x should be equal to v of x. This is also very intuitive. So another consequence of this thing, right? If an operator commutes with Hamiltonian, we have like so-called commutation theorem. They can be diagonalized simultaneously, or they have the simultaneous eigenstates. And h psi n of x is equal to some en psi n of x. And so I can apply parity, like let's apply parity on both sides. So it is pi. So this is just a number. I can go over the numbers and apply it like this. And here, because they commute, I can just carry this over here. So this is going to be h pi of psi n of x is equal to en pi psi n of x. So what we proved is if psi n of x is an eigenstate, pi times psi n of x is also an eigenstate. But I know what this thing does, right? Pi psi n of x is equal to plus or minus psi n of x, because these are the eigenvalues. And from here, right, I have two options. My eigenstates are either even or odd, right, because of this condition. So because of parity, okay, if it is plus, right, we call it even function. If it's minus, we call it odd function. Psi n's are either even or odd. Okay, that's also kind of trivial. And lastly, the consequence of this, if parity and Hamiltonian commutes, I can look at the expectation value of parity, d dt, and from the generalized Ehrenfest theorem, we know this is I over h bar, expectation value of h pi. But we know this is 0, then this is also going to be 0. And the meaning of this is if you start with a certain parity, that parity does not change in time. Right? If you start with even functions, as time evolves, you'll only have even functions, and vice versa. Yes?
What do we measure here? It's parity, so...
So here we don't measure anything, right? That's the trick about parity. Here we are saying that we are assigning, if you want, a sign, if kind of like a charge. Suppose I assign plus 1 for even functions and minus 1 for odd functions. This plusness or minusness will not change in time. And you can always calculate from this expectation value. But it is not a physical object, right? It's not like a physical charge.
Experimental so it can be measured.
Exactly, it is Hermitian, but there is no observable for parity. Like as far as I know, it is a symmetry, and of course, in particle physics, I'll talk in a little bit. There is like so-called parity conservation, but it's not like you have like say charge and Coulomb's law. You don't have things like that. So this is also the difference between classical mechanics and quantum mechanics. This is a little bit too much detail, but if you don't understand it, do not worry. So in classical mechanics, discrete symmetries do not yield any conservation law. Only continuous symmetry. So there's so-called Noether's theorem. If you don't know it, you can forget it immediately. But in classical mechanics, discrete symmetries do not have any conservation law. But in quantum mechanics, you can see there is a conservation law, even though the symmetry is discrete.
So, but you just said even though it is conserved, it's not giving us a quantity like momentum or energy.
Like, yeah, exactly. It's not like momentum or like energy, but when you compute things, you have something conserved in your equations.
But what do we call this thing? Like
I call it parity. That people call it parity conservation. So it is not like some physical object like charge, but it's still conserved. Evenness or oddness, right? If you want how your particle, what is parity? X goes to minus x, right? If you want how your particle behaves when you put it in front of a mirror, is conserved in time. Okay. So let me give you an example. So let's consider quantum harmonic oscillator. So that's what happens in practice. So we have like some Heidegger operator, which is 1 over root 2 h bar m omega minus I p plus m omega x. And you can see under parity, pi dagger, a dagger or a pi, because p goes to minus p, x goes to minus p, so this thing is going to be minus a dagger. And let's think about an eigenstate. So we have this parity hitting on, let's act it on n plus 1, and you'll see why I choose this n plus 1. So this is equal to parity times a dagger n. Right? There's an overall normalization, but that's not the point. But the parity can jump over this, and because of this, right, what does this tell me? This tells me a dagger pi is equal to minus pi a dagger. So I can jump over and pick up a minus sign. So this is minus a dagger pi n. And if we start here, if pi n plus 1, okay, this is if, is a plus sign with n plus 1, right? Because it is either plus 1 or minus 1. Let me write it a little bit cleanly. This immediately tells pi times n should be minus 1, right? Because of this minus, it has to come from parity. So this is n. And that means the states in the spectrum alternate, right? They are odd, even, they alternate as you go through the spectrum. And that's what we have in the spectrum, right? We have like ground state, which is symmetric in Gaussian, and first excited state anti-symmetric, and then we have this second excited state, and so on. And they always oscillate even, odd. Okay, good. Any questions? So in just a little bit, I'll show you, okay, just to be prepared, I'll show you when we consider angular momentum L and YLMs, this is actually going to be the opposite. Okay? So this alternation is actually not always granted, but you'll see what I mean in just a little bit. Any questions?
Do we require symmetries to be Hermitian?
Like symmetries do not have to be Hermitian, right? They are unitary. Think about translation. T dagger is not equal to T. T dagger is actually translation in the opposite way, right? But in the case of parity, it happens to be so. So it can be, but not always. So let's think about 3 dimensions, which will be a little bit more interesting in my opinion. Yes. Yes, they are unitary, otherwise it cannot be symmetry, right? A symmetry should conserve the inner product, and for the inner product to be conserved, it has to be unitary. So let's think about this pi acting on now a 3-dimensional wave function. And our definition was, this is going to be some psi prime of r, and this is equal to psi prime minus r. Good? And in 3D, we have pretty much the same behavior. R goes to under parity minus r. P under parity goes to minus p. And let's also think about angular momentum. Angular momentum is L is equal to R cross P, right? So L under parity, what does it go to based on this? What's that? Itself, right? Because R minus R, P minus P, 2 minuses are going to be plus. So this is going to be L. And it seems like, right, R is our familiar vector. It changes its sign under mirror. P is also a familiar vector. It also changes its sign in the mirror. But L, even though we put a vector, it behaves a little differently, right? So this is not like what we are familiar. And whenever this happens, we call these pseudo vectors. It is a vector, but it does some unexpected things like this. Yes? Oh, yes, yes, thank you. This is not prime, yes. Yeah, thank you. So pseudo vector means, what is that? So this is, let's think about pi, dagger, L, pi, okay, this is pi, is equal to still L, and I multiply both sides with pi, and I obtain this relation, right? Pi L 0, or if you want, L pi is equal to pi L, and you should compare this with harmonic oscillator, right? In the case of A daggers, we pick up a minus sign. In the case of L, we don't pick up a minus sign. Right? This is sometimes the definition of pseudo vectors. If a vector, okay, this is L, commutes with parity, we call it pseudo vector. And because now we have like a new operator in the set, our full set is going to be, previously we had L squared, LZ, and we can also put pi in the commuting set of operators. Any questions? So I want to, okay.
Does that mean that pi L can only have eigenvalues of 1?
So yeah, it's either eigenvalues of 1 or plus 1, and you resolve the Hilbert space in 2 different parities. That's what it means. You either have like even section or odd section, and they are separated.
And they're not like in the harmonic oscillator case. They're not changing.
They are not alternating. Yes. Now, let me mention that. Now I want to, okay, through an example.
Can I ask one? When we said that, when we take the time derivative of the parity operator, we said that it's not changing time. If you start with the parity, you will end up with the
Yes.
In the harmonic oscillator case, we said that the parity is because...
No, or you also have the same thing. If you start with like an even state,
yes.
That state under evolution can only be even, right? So we are going to see there will be so-called mixing. This state can never transform to this state. But it can transform to next one because parity is conserved. Of course, if you break that symmetry, it can be, but as long as you have the symmetry, these two will always be in isolated universes. They will never know about each other because of symmetry. In the angular momentum case, this is also the case, right? How do we label this? So we label this L, M, right? And each L, if you want, we call it a manifold. Now we are putting the parity and we are saying that L positive manifolds and L even manifolds, they do not mix with each other. That's what we are saying. So they are isolated. So let me try to be a little bit concrete. So what I want to show is the following. So when you apply this parity to Y, let me just use YLM because the radial part is irrelevant. LM, theta and phi. So this is minus 1 to the L, Y, LM, theta and phi. So you could deduce this purely from the definition of these functions, but I want to give you an alternative demonstration. So because L and pi commute, right? That means L plus or minus, they only have Lx and Ly, also commute with parity, right? So this is also to be compared with harmonic oscillator. In the harmonic oscillator, you pick up a minus sign, which is harmonic. A's and A daggers are raising and lowering operators, but raising and lowering operators of angular momentum do not pick up a minus sign. And what does it mean? So as you apply this L plus or minus, you change M, right? Only M changes to plus 1 or minus 1, but L is fixed. Because this operator commutes with parity, that means whatever your parity is, as you apply L plus or L minus, that parity should not change. Okay? So that means parity should not depend on M. Each given L has its own parity. If this is so, I can just use YLL. Why? Because YLL, it was so simple, we produced it in class in 5 minutes. I think if you remember, we said if you apply this L plus, this is 0. And from here we obtained YLL was something like e to the L phi sine L of theta. Now we can apply parity to this function, right? This is the form. There is like normalization function, normalization constant, which is irrelevant for parity. So with parity, phi and theta, or let me write the other way. With parity, theta and phi will go to pi minus theta and pi plus phi. I showed this last time graphically, but if you have any doubts, you should draw a picture and convince yourself this is the case. Then if you plug this in, I have e to the I L pi. Actually, this it's e to the I L phi, and I have sine pi minus theta to the L. And if you open this, I think I opened this like sine pi cosine theta minus cosine pi sine theta, something like that. And this one I put minus 1. From here I deduced YLL goes to, under parity, minus 1 to the L YLL. And from here I deduced, because it doesn't change with M, this happens for all M's. If I can deduce it for one L, because of this conservation, or this commutation, I know this is the case for all L's. This is okay. This is L, so this is M. Good. So this one is 0. So is this plus?
Oh, that's minus 1.
This is right. Minus 1 is plus. and there's only one minus coming here. Yes. Good. Now, okay. So what did we do? We introduced the symmetry, and it was the parity, and we showed it is conserved. And now we are also going to introduce last piece, which is the selection rule. So let's mention something called parity selection rule. So I am going to introduce an operator which is going to be important, but at the moment it's not important. The point is, like, we have like so-called electric dipole, and this object is going to be key for us to understand radiation, if we can get to there. But the form Griffiths uses P, but P is a little bit mixing up with momentum, so I decided to use D, and I will just put E for electric dipole. So the definition is electric dipole is charge times this R. So this is also a vector, an operator. If you want, it's kind of ugly, but just to be safe, I can use this notation. And because so Q is just the charge, R is the only operator. So this pi dagger electric dipole operator, pi, is going to be minus D, right? Because R goes to minus R, so this is minus E. So now what I want to do is, like we said, for any operator in the Hilbert space, we can think about matrix representations. And matrix representations typically determine what happens in the experiment, like what radiations, what transitions happen. But for the moment, let's just focus on matrix elements of this, this operator. And I want to consider, right, this is like three-dimensional hydrogenic system. So I want to consider this N prime, L prime, M prime, D, E, N, L, M. So this is the expectation, or like this is the matrix element between two most general states. And if, right, I can use this here, I can just write exactly the same thing like this, put a minus sign here, and introduce these pi operators. So this is pi dagger, so this is pi. Good. But I know what pi does to these hydrogen orbitals. So this is minus 1 to the L. So this piece here, if you want, including the pi, minus 1 to the L prime. And I have one more minus 1 here. So this is this entire thing, minus 1 to the L plus L prime plus 1 times itself. Good. Now I can take this one and this one in the same side and set the other side to 0. What I mean is 1 minus this thing, parentheses, times this thing is equal to 0. And now, right, there are like two factors, something times something else is 0. I have either this one 0 or this one 0. Right? And if this one is not 0, right, suppose if L plus L prime plus 1 is, so this is, when is this non-zero? Is odd, right? If this is odd, there's 1 minus 1 is going to be plus, or, so this is equivalent if L plus L prime is even, then the matrix elements are going to be immediately 0. I don't even need to calculate that. Good.
Isn't it supposed to be even?
If L plus, yes, if L plus L prime is even, right? If L plus L prime is even,
And this is all, if it's all, it's minus 1, if it's minus 1,
so it is like minus 1 to the L plus L prime minus 1, right? There is also plus 1 here. So this piece is 1 because of it's even. 1 minus 1 is 2. And if this is not 0, this should be 0,
okay.
right? So that's what we are trying to see. And yeah, for the moment, this is just like a fancy result, right? But later, when we try to understand like transitions, this will be important, and there's like a name for this. This is so-called Laporte's rule. I don't know how to pronounce, but let me just Laporte's rule. Did I skip anything here? No. Good. Any questions?
John, does this somehow mean the operator changes the angular momentum?
Does this mean?
The operator changes the angular momentum because if it is equal to L prime,
Yes.
it's going to be even, and then that's going to be even.
I mean, operator definitely changes the angular momentum, right? There is like R here, and it, right? R is XYZ, and XYZ are, you can write XYZs in terms of L is equal to 1. So it increases the angular momentum plus or minus 1. Yes, it does. But what we are saying is, of course it does it, but we are in the most general case, whenever the states in two sides are different by even angular momenta, they don't have any matrix elements. Okay, so this is the normal angular momentum. I want to now consider spin angular momentum, which will be like kind of like a repetition of what we did, but let's consider spin. And the spin is also angular momentum because it obeys the same algebra, so we expect it to have exactly the same behavior. And if it has the same behavior, we anticipate this psi dagger S or pi dagger S pi to be equal to S, right? I just copied the result for L and replace L with S because it's exactly the same relation. Therefore, pi and S should commute. And so we can think about this in two ways. We can think about the most general state in Hilbert space is like what? A times up plus B times down. And we want to understand the matrix representation of pi, right? If you put pi, what does it give? But S, in the case of spin half, let's think about spin half. S is h bar over 2 sigma, and sigma are Pauli matrices. And from here, I deduce pi and sigma commute. Good. That means each, right? This is like a vector identity. For this to happen, pi should commute with each Pauli matrix for J is equal to X, Y, and Z. Good. And here's the magic with Pauli matrices. So any matrix, right? Take any matrix in this 2 by 2 Hilbert space can be written like some A times 1 plus some B times sigma. Okay. How many people know this result? Like in the 2 by 2 matrices, right? Any 2 by Hermitian or not, any kind of matrix in 2 by 2 matrix can be written in this form. maybe I can give you like an exercise, think about this, and maybe we can have like a, because this is so important, we can have a quiz about this. This is exercise. If you want, you can just open up, right? There are like 4 elements. Write A, B, C, D, and try to find A, B, C, D in terms of these B vectors. And that will prove you that you can write any matrix in this form. But we are also saying this, right? This is also a commutation. Then, okay, this thing commutes with everything, so I don't even need to write. So this pi sigma j is equal to, how do I write it? Let me write it one by one. Bx sigma x plus by sigma y plus bz sigma z sigma j. So this should be 0 because of this symmetry we have. And if you take j is equal to x, right? Sigma x commutes with sigma x. What you are going to have is like something like by, I think, we also know the commutation of these matrices. This is like 2i sigma y sigma x is going to give sigma z plus bz something like 2i, it could be plus or minus, but it's not important, zx sigma y, so this is 0. And if this result is 0, what can we say for by and bz? So these are, if you want like unit vectors around z and y. If you have like a unit vector like some a times z plus b times y hat is 0, each component is 0, right? From here we deduce by is equal to 0 and bz is equal to 0. And if you take j is equal to, for example, y, you are going to find bx is also 0. Okay, so this is a lot of words, but at the end what we found is in this spin-off Hilbert space, parity is proportional to a times 1, unity. And because it doesn't do anything, we can assign any number, right? Because it just numbers just go through everything else. And typically, if we are talking about electron, we assign +1 for that. And I mean, for us, this is the end of the story, but in the future, if you take field theory, for example, there you'll have to solve so-called Dirac equation, and the Dirac equation requires additional structure. And there you are going to find, for example, so this is electron, and -1 for positron. So this, we have nothing to do with this. I'm just like saying so that you can be aware in the future if you have appetite in that direction. Good. Any questions? Yes.
I didn't understand what is conceptually doing.
Conceptually, what we are doing is like spin doesn't know about parity, right? For spin, parity is like a identity. That's what we found. And whether you give it like a, right? The parity is conserved, but that conserved charge, whether it's plus or minus, if you only have electron, doesn't matter. That's what we say. So for S, for spin, there's also a parity, but we don't have this relation for spin, right? So that's what we are saying. So spin just trivially goes through parity, if you want, at least for us. Good. Let me give 2 more notes, again for like future reference, because in this course, parity generally is not emphasized, but in the future when you take field theory and things like that, people talk about parity all the time. And it's important, but we don't need it at the moment. So we have like a vector. We can also introduce a scalar. So a scalar C does not change under rotation, which we'll introduce in a little bit. But since we, maybe next week, since we are right now talking about only parity, the scalar C does not change under parity. Right? Like if you have parity and C, parity, this should be C. So that's the definition of scalar. And the additional property is it should also be rotationally invariant. But we are not there yet. But sometimes, right, exactly like vectors and pseudo vectors, we can also have pseudo scalars. There are some scalars have actually not this behavior, but they have this behavior. So it's scalar, right? It doesn't have any direction and the sense of direction, but it changes sign. If we see things like this, we call this pseudo scalars. An example, I can just make up an example for this. For example, if you have P dot S, right? Because of dot product, this is like a scalar. S doesn't change under parity. P goes to minus P. With parity, this goes to minus itself. That's why we call this pseudo scalar. And this is sometimes what we call spin orbit coupling, but it's not important. It's just an example at the moment. And one last piece of information, I'll finish after that at this topic. So in E&M, right, we have electric field and magnetic field. So how does, if I put my electric field in front of mirror, what should happen? E should, does it change or does not change? So E, if you want, you can think about Gauss's law, right? Del dot E is rho epsilon 0, let me not write it. Under parity, charge is charge. You cannot change charge. Gradient should go to minus gradient. To compensate this unchanging charge, we need to have E goes to minus E. So with parity, E goes to minus E. With B, you can think about, del dot B is 0. This is not going to help you, but you can use del cross B, which is going to be nu 0 times J. And J is what? J is rho times V. So under parity, V goes to minus V, right? Because P goes to minus P. Nabla goes to minus nabla. There's only one minus here, right? To agree with right-hand side and left-hand side, B should go to itself. So that's under parity. And another interesting so-called pseudo scalar is like, for example, people call E dot B term. If you look at E dot B, right, this is like a scalar, but under parity, this goes to minus itself. But this is why we call it pseudo scalar. And this also makes sense, right? Why E and B changes like this? We can think about Newton's law, F is equal to m times A, which is equal to Q E plus V cross B. I know immediately how A changes, right? Because there is X inside A goes to minus A with parity. If A goes to minus A, E, the electric field should go to minus E, because Q is just charge. So V goes to minus V, and there's only one, okay, this is minus, so this is minus. There's only one minus on the left-hand side, then B should go to itself. Okay, this piece we don't need, but it's so easy I couldn't stop myself from talking about it. Okay, any questions? Okay, so second hour I have a quiz. It's going to be the first one, but I'll let you collaborate. Okay, thanks.